this talk is indeed about Isabel and Big Math, or rather ITP, interactive theory improvers, and Big Math. And so first, let's start with what is Big Math. So when I first heard the term, then my first association was big oil. That's not really what the term is about. It's more related to big data. So it refers to math developments that are really huge, that probably exceed what one single individual can understand. So things like classification of the finite simple groups, or something that I think is being undertaken now is proving Fermat's last theorem, something like that. And it is actually a term coined by lots of people who are in here today, like Michael Kohlhase, Jacques Carrette. I haven't seen Florian Rabe yet. Not sure if he's... Oh, there it is. I just didn't see him yet. So all those people in that paper, Big Math and the One-Brain Barrier, the tetrapod model of mathematical knowledge. And this is what I'm referring to here. And actually, in that paper, you identify the 5 central aspects to math that need to have computerized support to deal with these kinds of big math problems. And so those aspects are inferring mathematical knowledge, computing with math objects, then building concrete instances of abstract math objects, and in particular collecting them and working with collections of them, narrating mathematics, and finally organizing math knowledge. And today computer support exists already for all of these aspects, but typically in different systems. So for example, to compute math objects, you will probably refer to computer algebra systems. For collections of concrete objects, you have projects like the online encyclopedia of integer sequences. Don't worry, that's just that's coming back. And so we have all those individual environments of doing these things, and my claim here today is that actually interactive theory improvers, in particular Isabel, are environments where we deal with all those things. Because in essence, interactive theory improvers are an environment of doing mathematics, and so they kind of need to support all these aspects, or at least it's very helpful if they do. And I'm using Isabel. Sorry?
Why is it called a tetrapod model?
It's called a tetrapod model because how these things interact with each other, so I left that one out for brevity. But organization basically sits in the center and connects all these instances. And, I practiced. So that's the tetrapod.
And it has kind of this circumscribed, right? But think of a jack or so. And this is orga.
Yeah, and I'm going to look at these in the example of Isabel, because, well, I'm wearing this shirt, and also it's quite a holistic system, you could say. Anyway, so let's start with the obvious one, inference. So this is the aspect that ITP systems are typically associated with in this model, because obviously that's what they specialize for. And in Isabel, this is obviously when you prove new propositions from existing ones. So obviously there's tons of methods, tactics, automation to do all of that. In particular, there's Sledgehammer, which is a very nice tool. You can just give it any proposition and it will try to find a proof for you, and actually very often succeeds, even though you might think it wouldn't. And then there's also other tools, for example, to generate some counter models in nitpick here. Yeah, what is not yet supported though, but also finds under this inference aspect, is creating new conjectures from facts and examples. So this is the big one that we're missing right now, and in principle you could do this in Isabel, so you would have to obviously build machinery for that. And I know of people who are interested in that kind of topic, but so far we don't really have any implementation that would support you in doing that. So this one is missing. Yeah, next aspect is computation. So obviously the most efficient computation system are computer algebra systems. But it's also a very natural thing to do in interactive theory improvers. So computing in the inference kernel, if you have one, that's something that you can do. That's typically not very efficient, right? Because just doing all those very simple rewrite steps with representations that aren't efficient, for example, unary representation for numbers, that certainly doesn't work for anything large. But there are ways to do better than that. So, for instance, in Isabelle, what we do is from our definitions we create code equations. So, which are equations that you prove. So, you relate your abstract mathematical specification to something more concrete that you can work with and prove that. And then for new things that you define, you can often, just by composition, you already have executable code or are really close to it. And then that code, you compile it, you reload it into the UML process and run it. And with that, you can actually prove new theorems. So, for example, there's the approximation method, which does exactly that to work with real numbers. The one caveat, though, is that your proof now might not actually go through the inference kernel anymore, because we just said that was not efficient enough, so you have to trust some external oracle that by the execution of the code you trust that is a correct result, but you don't have an actual proof in terms of an oracle. I think this is mostly fine, though, because, well, you have to trust the ML system of Isabelle anyway. So there's a little bit more work that goes into these translations, and their things could fail, but in principle, you always have to trust your ML process. So no way around that. Yeah, there are also tools that utilize these code equations, for example, quick check to find counterexamples. And all of this working with executable code, that's not just toy examples. So sometimes people build really sophisticated thing of that. A great example is in the FlySpec project here, where this definition of an enumeration of tame graphs is being used to prove the property that all the tame graphs that are in the archive by Thomas Hales are actually all the tame graphs are in there. And this was done in Isabelle by actually going through all the graphs and picking out the tame ones to actually prove this conjecture. And it turned out that there was a bug in Thomas Hales' code to produce this archive, so very good that this verification happened. But in order to actually compute this enumeration, you would have to go through 2 billion graphs. So that's quite a lot. But that could be done in Isabelle. So this is the paper where this is described. Next up is concretization. And so first of all, for interactive theorem provers, things like theorems are already concrete objects, right? But that's not really what we mean in mathematics when we say concrete objects. There we mean more like concretizations of some abstract definition, which are more like examples. So my answer to concrete objects is kind of twofold. So you have all the objects as concrete objects, and we do things in that with Isabelle. So, for example, if you do your regular Isabelle builds, then some of the objects will be exported into some external database, so you can work with that. And it's also used internally then. So, for example, if you look at the HTML representation of a theory here, here you look at, I'm looking at the markup tree for fun here, then you can see, I mean, you can kind of badly see, but I can tell you that there you find all the different names of things, entities that are defined at that point. And so we do use them. What we don't really do is create any databases of example objects. So that would be fairly easy to do because we have all the machinery for that, and maybe that would be a good idea to do, yes.
Why are they all nested within each other?
Sorry?
Why are they all nested within?
Well, so they are all nested in there because this is the source position where all of those entities are created, and this is the keyword here, which you can barely read as fun, which is from the function package. And in Isabelle, when you define a function as a term of equations with pattern matching, then under the hood a lot of translations happen to actually embed that in higher order logic, and so a ton of things get defined. And all of the things get defined at that point, and this is why they're all nested in this big one-markup tree to display that, well, they're all at that point. So in the end of the tree, you would see the fun here. Yeah, so this is about concretization. The next aspect, which I think is really underlooked in ITPs, but it's also really important, is narration. Sorry?
Can I ask one more question about this concretization?
Yes.
So what does this whole mass of HTML have to do with concretization?
So this is a representation of the concrete objects that, in terms of in theorem prover, not concrete objects in terms of examples, that gets created when you run Isabelle, is stored in a database, and is then used to do something with it, namely process this HTML. And the effect of that is that if you have a reference to that somewhere else in the markup, then you have a link where you can navigate to that.
Okay, then I think I don't understand what you mean with concretization. Because first you said, okay, theorems are already concrete objects, but that's not what you meant.
Yes, so this is the mismatch between the tetrapod model and what ITPs think of as concrete objects. So in the tetrapod model, a concrete object is one example of a more general abstract mathematical structure.
Like you have groups and you have...
Yes, and you have one specific group. So and collecting all the groups and categorizing them, that's an example of concretization in the mathematical sense. And then in interactive theorem provers, you have a more general view of concrete objects, which is used, but what we don't do is having any database where we collect those concrete instances pertaining to those groups.
So is that HTML stuff an example of tetrapod concretization?
No, this is an example of ITP concretization, which could be tetrapod concretization, but currently is not. Florian.
Yeah, it's not surprising that there's confusion about this one, because that's the one we have struggled the most with coming to a common intuition for.
Yeah.
And the way I see it now, and it might not even agree with the other co-authors, is what you showed on the previous slide was quick check and the tame graph enum. That's what I would put as concretization. You have a type and you collect individual or a large mass of examples for it, either to make universal statements about the type or just have counterexamples for the theorems.
Okay, that is what I would put under computation, because there you actually use the system to actually compute something.
If you have large amounts of concrete data, you generate them with some algorithm.
Yeah.
Conceptually, I would put it as concretization.
Okay, good.
Is there an actual list of tame graphs in this one of these definitions, like tame enum or archive or something?
So this is an actual list. This is like a file that's being loaded, and this is just a definition. And with the executable code, you can enumerate all.
So maybe they would say that archive there is concretization, and
Yes.
then the proving is the computation.
Yeah, perhaps.
My question is, you said it would be easier to do this database of specific examples. So, 3 is a natural number, and
Yes,
some
yes.
of them you want to list. Are you thinking of doing that?
Not necessarily
because for some
personally.
things you don't think it's very good, but for others you do think it's very good, right? Kind of for
Yeah, so I think it's quite easy to. So I think this kind of tools exist in the Platonic world, right? You could build it. It's clear how to build it, and it would be well supported. But currently, people aren't doing that, and I think it depends on. Are there enough people who really need that? So, for instance, when you have people who work on deriving new propositions from data within Isabelle, then you would want to have those kinds of collections, and then you would definitely need to build them. And otherwise, I'm just sketching how you would build them here.
Cool. Thank you.
Okay, one last question, then I want to go on.
Two very quick ones, and if you don't
Okay,
care
sure.
about answering them, fine. Do you have any sense of how large the tame graphs get? And do you connect to a software database, like a relational Postgres thing, or just?
So, how large the tame graphs get, I actually don't know. I would have to read up. It's described in the paper here. And then the second question, and yes, we do export it to a PostgreSQL database, which you can read and use. Yeah. And that's just...
You compress things, you don't have 58 gigabytes.
Yeah, we do compress things. If you run the normal build, you will only get the namespaces of things, but you can activate the export theory options in Isabelle, then you get all the foundational content, so all the terms and types, and all of that is in there as well, and it's not very large. I don't know how large the database are for like HOL, maybe Makarios now knows from memory, but it's not too large, so you can export all of that for the entirety of the AFP, which is huge. We'll get into that in a second, and it's not a problem. Okay, let's go into narration. So yeah, I think it's very crucial in ITPs that you don't just enter some hardly legible ASCII text and then have a few comments and maybe a proof script that the computer accepts, but you can't read at all. I don't think that this is really what doing math is most of the time, because usually what we mean by doing math is conveying intuition about the properties of objects. And so surely that's you can't do that by what I just described. They just give those intuitions to a computer and check if they are valid. But what you really want to do is narrate how do you arrive at these conclusions, what do they mean, how do things work. In Isabelle you actually do have lots of support to do that. So there are many document commands that are really first-class citizens in Isabelle. There are things like anti-quotations in here. So this on the left, this is all in the Isabelle editor. And you can see there are things like propositions in your document markup. You have commands for things like section, subsection, and so on. You have comments to control what gets printed once you print all of that. Because this is just markup, but you can also print it to PDF, which here you see the right-hand side, which is the print out of that source text here. And that is actually, so this actually works very well because you can just use markup to annotate your text. It does interface with LaTeX, so if there's something that isn't available as a markup, you can use the raw LaTeX, but often you don't need to. And that makes writing documents very convenient. And because you can then export it to PDF, you can actually write full papers with that and submit them to a conference. So this is something that people regularly do using Isabelle. For example, Makarios and I wrote a paper for the ITP conference in Isabelle, even though it didn't have any formal mathematical content. But yeah, that works great. I'm asking all of you to look more into the narration aspect in your theorem provers, because I think that this is really important. Okay, then the final one, which is organization. And so organization typically refers to how the content is organized within the system, so which kind of modularity systems there are. In Isabelle, we have the general source structure of which theories we have, which sessions of theories, and then internally we have locales as one big instance of a modularity system. Someone wanted to have an introduction on locales. Maybe someone can give that as in one of the slots this week. But I would also consider the external organization of how generally our developments are organized in here. I'm not sure if this is, if all the original authors agree with that, but I would put it in here as well. And in Isabelle, we have the archive of formal proofs, which is this huge theory archive, and how that is organized reflects the organization. So going into ITP libraries like the archive of formal proofs, we want to do big math, so let's see how big our libraries actually are. I'm only considering centralized libraries here, so sorry, no Coq or Agda in there, but rather I have as a few examples Isabelle, Lean, Misa, Holite, and PBS. And should the numbers here not be entirely accurate, then I apologize for that. Lots of them I had to collect myself, so I'm not an expert in all of these systems, obviously, so I might have not accurately reflected what is the case. So let's look at when the library started. So for those three, there is an official starting date. I couldn't find any official date for whole library in the PBS library, because I think they kind of emerged from the systems. Maybe there's an official starting date, but I didn't find it. So certainly those two are quite old. They exist for a long time. The AFP exists since 2004. The Miso Mathematical Library long before that, and the Lean Mathlib is obviously quite new. And then when we look at the size and the growth of these libraries, so by source size, actually the PBS library is the largest one. That is if you include the proofs, because in PBS the proofs are separate from the definitions, and also the proofs are kind of sometimes generated with a Lisp-like notation where you often have one brace or one parenthesis per line. So you can imagine that's not very compact in the number of lines. So you have 6 million lines in there, but only 150,000 lines if you consider only the definitions. Then in Isabelle we have about 4 million lines, Lean 1.5 million, Misa 3 million, and whole library just under 1 million. But yeah, as I said, lines of source code are not an ideal metric. Something that's much more interesting, I think, is how many user-specified theorems that are actually proven by a user in the system do you have. So the measurement method here varies across the system. This is why it's just approximate. For instance, in Isabelle, this is all instances of the keyword lemma or theorem, but obviously there are more than that. So this is just an approximation. And you have about 270,000 in Isabelle, 150,000 in Mathlib, and then much less of that in Misa, Holite, and PBS. So 70,000 in Misa, and then less of that in the other three. So by the number of, although I'm not entirely sure in Holite here, because there I counted all the theorems that are proven with proof. I'm not sure if that's accurate.
May I mention something about PBS? I don't know how you count the number of theorems that were generated automatically. But perhaps you count the number of TCC, type correctness conditions.
So in PBS, I counted the instances of where it's explicitly stated as a lemma. So this is...
Okay, yes, but most of the proof obligations that PBS generates, the interesting ones, should be discharged and discharged manually.
Yeah, so I'm not counting proof obligations here.
Then I think this number is approximate because...
and I don't mean intermediate steps in a proof. I really just mean top-level steps of a proof. So just the top-level statements that are proven, specified and proven by the user. That's what I call it.
I think the PBS community can help to define this number with more precision, because the type correctness conditions usually give the most amount of effort for this.
Yes.
The lemmas are simple, you prepare all for having lemmas and theorems covered by, but some of the proof obligations, this is the real work.
Yeah, certainly. And I mean, this is not a uniform methodology.
Yes.
I'm not sure if you can really have one, but if you include like every theorem there is, then I also don't think that this makes very sense. You get a lot of theorems that are simple intermediate steps. You get a lot of theorems that are proven purely automatically, and the user never even thinks about them. So there is a trade-off here. If you get into the number of actual theorems in terms of deducti, then for the AFP alone, you have millions and millions of theorems. So this is really just top level, because I think from a narration aspect, those are the theorems that are really important to people. But this is just a rough indicator of size. I'm not claiming that really in Isabelle there are, I don't know, 10 times as many theorems as in the PBS library. In the end, it depends on are those interesting theorems and not just the sheer size, which brings us neatly to the next point. And that is, we've seen how much mathematics we have in those theorem provers, but how much of actual mathematics is that? And I think that's an interesting question to have a short look on, but it's also quite impossible to answer, because there's no clear definition of what is math and how much math is in there, but we can look at a few indicators. So if we look at the top 100 theorem list from Frege-Wittig, then we can see that 90% of those are proven inside Isabelle. I heard you bring a new list.
On Wednesday there will be a talk.
On Wednesday there will be a talk, so I'm curious to see how many of those theorems are proven within Isabelle. Maybe you're going to tell us. Okay. Yeah, but the top 100.
So maybe you're going to tell us.
No, I'm not going to tell you, because I don't know what his list is. Okay, so yeah, they don't really tell us how much of math is proven. It's just 100 interesting theorems, so it doesn't really tell anything about volume. I think a better comparison is if you compare it to the archive size of informal mathematics. And obviously archive is not ideal here. I would prefer to use something like ZBMath Open or something, which is really a repository of mathematics only and not just preprints. But the advantage of using archive is that you get nice data for that. So this is why I have chosen that. And I'm comparing the math and computer science content with the AFP because there you also have math and computer science. And when we're comparing the sizes, then for archive, we're looking at the raw text, so just the content of the PDFs, and that's really a manageable number. That's 64 gigabytes of compressed data. It's not too much. Of that, about close to 40% is math and computer science combined, and you have about 750,000 individual papers. You do have to consider the De Bruijn factor, also introduced by Frege here. Namely, when you're doing a formalization, it usually blows up because you have to write about a lot more details than you would have to do on paper, and this De Bruijn factor is usually in the range of 1 to 10, and I've taken the typical 4 as an average here. Yeah, so then in the Isabelle and AFP, the theory source that you have it compresses about 85 megabytes or 830 entries. And now that we have the numbers, we can actually compare them, and we get to a factor of 0.1% of mathematics that we have as an equivalent size of archive. That's certainly not all of mathematics, but it gives you some indication. And actually, so the 0.09 number is when you compare the source sizes, and this 0.11 number here is if you just compare the numbers of papers and articles, and I think it's quite encouraging to see that they're so close together, so it tells us that something we're doing here is right in this comparison. And also, this is much more than I would ever have thought, 0.1% of archive. Yeah, this is huge.
Did you zip the files first?
Yes, they are all compressed. So because in the end we want to compare the information content, so you have to compare the compressed size. Yes. Yeah. So and that brings us to the next point I want to make. We have to formalize 1,000 times the material, right? If we ever want to get to the size of archive. But I do think that there are some problems with that. So certainly, theorem prover systems of today wouldn't be able to hand 1,000 times the material. And I want to briefly now look at what that would mean for systems like Isabelle. So the first thing that you have to do is obviously you have to host all of that material. Luckily, we're in the information age, so that's really not a problem. We can skip that. But once the material is hosted, you also do need to find it. And that's where things already get more difficult. Luckily, these days, there are some specialized search engines for theorem provers, like Google for Lean, or tools like FindFacts or Serapis for Isabelle. And I don't think, so if you want to scale up that search by a factor of 1,000, then you would have to investigate some effort there. I think so this is based on unification here, and that might get too slow if you have 1,000 times the material. I'm not sure, but certainly you're shaking your head, so hopefully it works.
Yeah, that's smarter. It would already have died if we're doing what you're thinking it's doing.
It
would already not be effective on math, but if
it would not be effective. Yeah. Okay, that's great to hear. And I think you could easily scale that up, so that's really not a problem. You can scale up the search. Now you have searched, you your material, you have collected together what you need for your formalizations, and now you need to bring it all together. And that's much more difficult in some systems. So if you're working with MATLAB and Lean, then hopefully that should be very easy, because there supposedly everything works smoothly with each other. So you just have to collect everything and import it. But with other systems, it's much more complicated. So, for instance, in Isabelle, you do have some technical problems still. So if you have multiple theories in your import path with the same name, that already doesn't work. Certainly that can be solved. But you have the fundamental problem in the AFP that it's more like a bazaar, what is in there, and the things that you get there don't necessarily work smoothly with each other, because there might be different representations of the same thing. And that's a fundamental problem, in particular, also with Lean, if you start to integrate different systems, as we've heard before today. So, luckily in Isabelle, there are some tools to help you deal with that. So there's transfer and lifting, which you can use to transfer theorems from one representation of some definitions to the other. That's quite helpful there. But they're not, those tools aren't as general enough, or are not as general as they could be, and you would probably have to improve the automation quite a bit if you really wanted to do all of that at scale. Thanks. The next problem is all of that material must actually work, so you can't have any broken proofs, things that don't even type check, and this is really difficult to achieve. You have to build all that material within your prover. So in Isabelle, we just finished some work to do that in a parallel way. So what you see here is a build schedule for the whole AFP on, I think, 8 different machines here. So this is the entire schedule, and that brought our build times, which were already exploding, down to less than half an hour, again, from 4 to 8 hours before. And we could perhaps scale that. So right now this worked for small clusters, but in principle you could have hundreds of machines that all work in the cluster and build much larger session graphs. So you would have to investigate quite a bit of effort, but that could work. The next big one is guidance and tooling. So these days there are some linters that help with that and tell people that which things they should definitely avoid, but you do need more of that tooling. So, for instance, what we don't yet really have as good tools is deduplication, so you do need clone detection to find those kind of clones and warn people in advance that what they are doing has already been done before somewhere. I think that would be very helpful. And then you probably want more tools, for example, to help people visualize proofs. I've seen a demo of a Lean tool that does this for geometric proofs. So you do need more help on that. And then my final point is you also do need to maintain all of that, and that's really difficult. So paper is always patient, but ITPs really are not. And we don't really have much tool support at all for maintenance. So what you need is tools that allow you to rename things across many different sessions. That's would be very difficult to do in Isabelle because all the tools manage their own namespaces. You would need IDE support to really edit a lot of stuff at once. So for instance, have an IDE where you can see what are the effects of your edits across many different sections without rechecking everything all the time, because that's far too expensive. And so lots of tooling would be required here. Recently, I just built a system that allows you to execute Isabelle builds on a cluster without needing to push things anywhere and allowing you to specify your own experiments. So that's helpful. And also doing automated builds. And I think we need a lot of tools like that to help us afford to go to that scale. And not just that scale, but also the next order of magnitude is where we need all those tools, I think. Okay, so I think I really run out of time, so thank you all for listening.